All right, let's test our LED with the M2K. We'll review. We just connect it. Give it a moment. Alrighty. Now down here, and this is our kind of abridged proto board. So we have an LED connected in series with a 100 ohm resistor, and it might look like it's into that hole, but really everything is along that hole. That's the ground of the M2K, and that is V2 minus. And so channel 2 is measured across the resistor, channel 1 is measured across the LED. This will be our LED voltage, and this voltage here divided by 100 ohms will give us the current. The signal generator can actually produce 5 volts or any constant. It can also do the waveforms, which we've seen. It can even read in a file, which we'll do later. And you can even do math. But let's just do with 5 volts, just like our simulation. Run, and we can see that the LED is on. Now let's look at the measurements. We have a voltmeter. All right, everything is 0. We run it, and now we're getting 2 volts, and that's across the LED. And we're getting almost 2 volts, and that's that voltage across the 100 ohm resistor. And so, yeah, we're getting almost 20 milliamps at 2 volts. But we sum this up, right? And where's the missing voltage? Right? Because if we put in 5, why am I only having 2 and 2? Well, that's across the 50 ohm series resistance. All right, which we talked about in the ltspice prior video. All right, let's go look at this in the XYZ domain. So we go back to the signal generator, click on waveform, 5 volts peak to peak, 2 kilohertz, right? And then we're going to go to the oscilloscope. And click run. And we can see that channel 1 is the input. Or channel 1 is the voltage drop across the diode. Channel 2 is the voltage across the resistor, which is representative of the current. Now, this rolling off here is because when there's a lot of current flowing through the diode, the resistance is becoming much less than 50 ohms, and we could be approaching the limit of how much current the kit can source and sink. Now over here is the XY plot, and you get that by, you click here, and there's these choices, FFT, XY, histogram. All right. And if you want to zoom in, right, you can click on the channel, right, and that's this voltage here. And if I increase that, I kind of zooming out. If I decrease it, I'm zooming in. All right, and if I want to increase this, I click on the scale for the channel 2. Oh, that's time base. Okay, that's zooming out, and this is zooming in. And if you can actually pull off IV pairs just by following along this curve. All right, it doesn't quite go up to where we wanted, so I have to go back to the function generator. I'm now sweeping it by 10. I go up to the oscilloscope here, and yeah, I need to move that down in order to see everything. Still a bit out of range. Oh, it's almost there. And there you can pull off that point. So you can test transistors like this. It's a little more complicated. And yeah, it's dependent upon knowing the exact value of the resistance that we're measuring things across. And if you want to measure smaller currents, you use a larger resistor. And there's test equipment, IV curve tracers and things like that, that automatically switch that resistance so that you can zoom in where you want. This is a bit of a hack, right? But you can see. Also, let's see. If you go back to XY, you can, this is plotted in lines. I can click on dots, and you can, these are now dots. If you want to see the dots, you would just zoom in. But there we have fully tested our LED. We can do a curve tracer. And now when we do our stochastic resonance project and we're trying to have an LED blink in time with the noise, we can do that.